Okay, chapter 21. We are making progress. An ordered integral domain is an integral domain A with a relation symbolized by less than having the following properties. For any A, B, and A, exactly one of the following is true. A equals to B, A is less than B, B is less than A. Furthermore, for any A, B, C, and A, you have these properties 2, 3, and 4. If A is less than B and B is less than C, then A is less than C. If A is less than B, then A plus C is less than B plus C, and if A is less than B, then AC is less than BC on the condition C is greater than 0. This was your first quiz question. Did we get it correct? Awesome.
Exactly one of them is true.
Oh, yeah.
I didn't write that one.
Yeah.
Oh, so you couldn't just say A equals B.
You couldn't just say what?
Because I just wrote A
One of
equals
the
B, A
following
is less than B. A is greater than B.
You do need to know exactly one of them is true, because otherwise you could say, 2 or 3 of them are true.
Well, I was just wondering since there was only 4 lines that I didn't know. So.
Yeah, I didn't count the number of lines the book made. I just assumed you guys could squeeze it in there.
I put 4 in there.
You still need to know, because an or could be both of them are true. You need to know exactly one of them is true. If you're in computer science, it's an XOR. You only have one of them true.
Yeah, I put or too. That's just grammar.
You need to know exactly one, because
Not there. He's talking about A equals B, comma, A less than B, comma, or B.
yeah, if you put an or right here, that's okay, as long as you have that guy right there. Yeah.
So in other words, no.
You have to have exactly one is true, because you could have an or that has both of the or statements being true. Yeah, only one of them is true. Okay, so let's think about this. Is Z5 an integral domain? What's the definition of an integral domain?
It satisfies the community property.
It's a commutative ring with unity having the cancellation property. So is Z5 a commutative ring? Mm-hmm. Yes. Does it have unity? Mm-hmm. Does it satisfy the cancellation property? Yes. 5 is prime, satisfies the cancellation property. So yes, it is an integral domain. Is Z5 well ordered? Is it an ordered integral domain? That's correct, but why? Yeah, what happens? You know that 1 is less than 4. What happens when you add 2 to both sides of that? If you do 1 plus 2, do you get that less than 4 plus 2? You would think so, but what is 4 plus 2 in Z5? 1. Is 3 less than 1? No. So it is not well ordered. It's not an ordered integral domain. So here's the next question. Can we have a finite ordered integral domain? No, because it will wrap back around on itself when it's finite. So no, if you're going to have an ordered integral domain, it has to be infinite. That's actually something that they end up showing sort of, they mention it in passing, and you end up proving it in one of your homework problems. Question.
How do you know something has unity?
Multiplicative identity. Any other questions on that? Okay. Let A be an ordered integral domain. Let A, B, and C be elements of A, such that A is less than or equal to B and B is greater than or equal to 0. Show that AC is less than or equal to BC. This is similar to your first homework problem. It is using our ordered definition of an ordered integral domain. So, what's the hypothesis for this? such that A is less than or equal to B and C is greater than or equal to 0. Now I have cases. Case 1, I'm going to have A is less than B and C is greater than 0. Under this case, I can go use my property, this one right here, number 4, A is less than B. Look at case 2. Case 2 is going to be A is equal to B and C is greater than 0. If A equals to B, C is bigger than 0, then I can definitely multiply both sides and keep the equality by our, it's not our cancellation laws, it's our multiplication stuff that we did when we were talking about groups. Where is that?
Case 1, if it's just less than, we can just write that it's less than. or equal to.
Yeah. Because that's a less than or equal to. It's an or statement. Satisfies one of the or statements. So yes, you can. I'm going to write it this way. A equals to B, then AC is equal to BC. Because C is just a fixed value and A equals to B, since multiplication is well defined. Question.
Why can you say that it's less than?
Okay, listen to the words as you're saying it. Less than or equal. If it's one of them, it satisfies the or condition. The or to be true is only at least one of the two statements is true. Think about P or Q. True or false is true.
So that
What?
means, so once you find it works for ones, you don't have to do any more cases, is that what you're saying?
No. I'm headed down to 4 cases.
Oh, you are, you still have to do it anyway?
Yeah, we have to check all 4 possibilities.
But
Because if it's wrong in one of the possibilities, then you can't say that it's always true.
I thought you said if one of them is true, then true or false is true.
When you're going from the strict inequality down, then it's true. So if something satisfies, tell me about this. If 1 is less than 2, is it true that 1 is less than or equal to 2? AC is less than or equal to BC as desired. Let's look at case 3. Case 3, I'm going back up to A is strictly less than B, but I'm going to say C equals to 0. Then I know that AC is equal to A times 0, but what is A times 0? We've proved that. 0. And BC is equal to B times 0, which is 0. Thus, AC is equal to BC equals 0 implies AC is less than or equal to BC because they're the same value. And then for the last case, we have
Should be
A equals B and C equals 0. Then, as before, let's put the comma next to the then. I know that AC is equal to 0 is equal to BC. And so AC is less than or equal to BC. Thus, if A is less than or equal to B and C is greater than or equal to 0, then AC is less than or equal to BC. You have 4 cases to argue in your homework problem too. Very similar cases. Any questions on that? Okay. In an ordered integral domain A, an element A is called positive if A is greater than 0. It's called negative if A is less than 0. And if A is greater than 0, then negative A is negative. So if you have A is positive, then we say when we put the minus sign in front of it that it's negative. However, if A is less than 0, then negative A is greater than 0. Okay? So make sure that you know what your initial value is for A before you put the minus sign in front of it to change the inequality. Okay, we have a lemma. In any ordered integral domain, the square of every non-zero element is positive. This is important. This is something that we have been using ever since we knew there were negative numbers. What is that, 4th grade? If you multiply it by itself, it becomes positive. So what's the hypothesis statement? Yeah, let A be an ordered integral domain. Let A be an A such that A is not equal to 0. And then we have 2 cases. Let's do the easy case first. A is greater than 0. Now, go back. If A is greater than 0, if I go back here, what happens if I multiply A by A? In other words, we want to multiply the inequality by A. If you have A is greater than 0, we want to multiply by A on both sides of that inequality. A squared is greater than A times 0, right? By property 4. I'm going to say A times A is greater than A times 0 implies A squared is bigger than 0 as desired. That's what we were trying to show. Now let's look at case 2. I'm going to have A is less than 0. If A is less than 0, then what is minus A? Greater than 0. And, as before, minus A times a minus A is greater than minus A times 0. Tells us minus A squared, let me write it this way, minus A squared. I've put both of the minus signs out in front, which we can do from our discussion of negatives 3 or 4 chapters ago. So I put them both out in front. This has to be greater than 0, since minus A times 0 equals 0. But what is the opposite of A squared? Additive inverse of the additive inverse, if you will. It's the original. That's what I wanted to show. I wanted to show that A squared is greater than 0. So let's draw a conclusion. Thus, for all A in A squared is greater than 0, and we are done. Oh, yeah. For all A not equal to 0. Forgot about that guy. If it's equal to 0, then you have to put a greater than or equal to sign on it.
Second case doesn't seem that much harder than the first.
It isn't. You just have to be careful to factor out the two negatives. Group them together, because they'll cancel. Any questions on that?
Did we just use that definition for case two?
What definition?
The definition I think.
Of this one right here? Yeah. I did. Okay, you guys have a classwork problem. In an ordered integral domain, the unity is always positive. This one is actually proved in the paragraph in a book. It wasn't written as a lemma and with a proof symbol around it, but it was written there. It is one sentence long. You need to get in groups of 2 to 3 people, or 3 to 4 people. Looks like 1, 2, 3, 1, 2, 3. Yeah, 3 or 4 people. That means that's when you're gonna have to find a group because you're by yourself over there. So this is in the bottom of page 209 if you're looking in the book for it. Just this right here. Not any of the rest of the stuff. We're gonna get to that together.
You said that the unity is the logical identity.
Mm-hmm.
So for example, in Z5, so anything comes out.
But a matrix is it's a matrix.
So if it was the matrices, would it be the zero matrix or no? But that's additive.
It'd be 1, 0, 0, 1.
Oh, okay, okay. I see.
Mm-hmm.
That makes sense. So is it always gonna be one though?
That's why we write it 1 sub A usually, because we're trying to get you away from thinking that it's always equal to the number 1. You could have in functions it's not 1 at all. There's no 1 in it. Well, it depends on your operations for functions. If you're doing addition and subtraction, then it's f of x equals to 1. Addition, multiplication. But if you're doing function composition, then it's something else.
Probably because the square itself.
Yeah.
The square itself is positive.
Yeah.
The square of the unit equals itself.
I guess, should we start with like, let there be an ordered integral domain A?
We never say let there be light. Let A be an ordered integral domain.
prove what they just state here?
That is the proof. They state it, but it is the proof.
Do you have me to start from here? Yeah. Oh, whoops, I thought you were telling me to start over here in this line. So where do you want me to start? I don't think we'd have to state it such as I'm saying.
It is literally one sentence. It really honestly truly is one sentence.
Because that's just comes from this.
Well, comes from
Yeah, this comes from this.
It's the last paragraph.
So I'm wondering if we
It's the single sentence paragraph, second to the last from the bottom of the page.
Just put any positive integer and that's it.
On page 209,
Yeah.
it starts with in particular.
One equals that's it.
That's it.
But I thought,
What you thought? Well, what do you know already?
Right, this is the next guy.
You know, yeah, your hypothesis, let A be an ordered integral domain, you know 1 sub A has to be in it because an ordered integral domain contains the unity element. And you know that 1 sub A times 1 sub A has to be equal to 1 sub A, right? So you know. And then by the previous proof that I just did, the square of any element is greater than 0, and you're done. It really is just one sentence.
we have to say let A be.
Let A be an ordered integral domain. So I see you guys are making Lubeth write it all down. Have you contributed to her knowledge? You're not checking what she's writing to make sure she's not telling me about her pet cat?
Check her.
Oh, okay.
So if you say like letting I sub A be an A, does that imply that you're saying that's the unity, or do you want to specifically say the unity?
Unless you're using the symbol 1 sub A, then you have to say it's unity. But we always use 1 sub A for the unity symbol. Or in some cases, just the letter, the number 1. Yeah. Okay, I think everybody's done, so let's continue. Notice that if 1 sub A is greater than 0, you can see that n plus 1 times A is greater than n times A. This is by induction. That would be a proof by induction on that. It's an inductive argument. You actually have a proof by induction that you're going to do in your homework. It's the last one, I believe. We're not actually going to go through this one. That's a very straightforward inductive argument. In any ordered integral domain A, the set of all the multiples of 1 sub A is ordered as in the integers because you get it from right here. So if you have the negative, you have negative 2, 1 sub A is less than negative 1 times 1 sub A is less than 0 times 1 sub A is less than 1 times 1 sub A. And it keeps on going. So it's ordered like the integers. You have a negative 2 of them, negative 1, 0, 1, 2, and so forth. That means that there's an infinite number of them because there's an infinite number of integers. So there's another argument for why your ordered integral domain has to be infinite. It cannot be finite. In any ordered integral domain A, the set of all the multiples, we read that one. Notation, the set of all the positive elements of an ordered integral domain A is denoted by A plus. And this guy's going to be important in the arguments that we're going to make following. An ordered integral domain A is called an integral system if every non-empty subset of A plus has a least element. That's also the well-ordering property. So let's look and see, are the integers an integral system? Think about any subset of the positives of the set of positive integers. Does it have a smallest element? Think about the set of natural numbers. Does it have a smallest element? Yeah. The even natural numbers, does it have a smallest element? 2. The odd natural numbers? 1. Yeah, it has the smallest elements. So yes, the integers are an integral system. Are the rational numbers an integral system?
You don't know what the smallest one is.
Yeah, suppose I had said you're looking at 1 over n to infinity. These are all on that interval. Those are all positive natural numbers. But what is the smallest one in this interval? Yeah, it doesn't have a smallest value. It goes down to 0. It approaches 0. Its limit is 0. But 0 is not a positive number. It's 0. So it does not have a smallest value. Pen stopped writing. So this one is going to be no. And then are the real numbers an integral system? Same reason, no. Keep that in mind because we're going to be using that property. In any integral system, there is no element between 0 and 1. So let A be an integral system. Yeah.
If you have an integral system based off of something like 1/2, they go up in halves.
Yeah, discrete values that, yeah. If you have a discrete fixed distance between each of them, yes, you can. But you can't have something like a 1 over n then. So you can't have like 1/2 to the power n either, because that distance gets smaller and smaller between them.
A half.
Yeah, if you wanted to look at a plus 1/2, a in the naturals, or in the integers. The problem is that when you multiply the two values together, then you get an a times a 1/4, and that changes the distance between your numbers, gets smaller and smaller. If you did a times 1/2, square it, and there is the problem, because that's driving it to 0. You can't have something that has a 0 limit. that distance has to be fixed between it. Okay, so A is an integral system. Now, what we're trying to do is get to show that there is no element between 0 and 1. Let's suppose there is. Yeah, that's exactly right. Now, these are the additive and multiplicative identities of A. So 0, the additive identity, is going to be less than our A is less than our multiplicative identity. What does that tell us? If A is bigger than 0, then A is in the positive set of elements for our integral system A, right? So by definition of an integral system, I know there has to exist a C in A plus such that C is less than A. How do I get that argument? Well, actually I can go this direction. No, I'm going to go this direction. This is the direction I started. Let me go C is less than or equal to A. It has to have a smallest element. I might have chosen the smallest element in choosing our element A. But what I know is that 0 is less than C is less than or equal to A is less than 1. What happens when I multiply? Multiply these right here by C, I get 0A times C is less than C squared is less than or equal to C times A is less than C times 1. I just multiplied it across on the inequality. Simplify this. What is 0 times C? 0. C squared, and that's going to be less than C times A. Well, I'm just going to go straight to C times 1, which is our C. That's all I really care about. But C was the smallest element. I should have put this up here, is the smallest element of A plus. That's the argument I'm using. C is the smallest element of A plus. So this gives me a contradiction. What's my contradiction? You guys see that? Yeah. C squared is smaller than C, which was the smallest element in C plus. Thus, there is no element between 0 and 1. Let's see if I can write that better. Now, if you recall, the whole point of this section is to come up with a construction of the integers. What do you have to know to be able to say this will generate the integers and only the integers? Well, it generates isomorphic to the integers, as we're going to see, but essentially this gives us our integers. There's no integer value between 0 and 1 on the integers. In any integral system, every element is a multiple of 1. This is the theorem I was looking for last week, on Thursday last week. In any integral system, every element is a multiple of 1. So let A be an integral system. And we need to get an element A and A. Now, what we want to do is prove that this A is equal to, our goal is to show A is equal to n times 1 sub A for some n. That's what we're trying to do. That's our goal. So what we're going to do is we're going to suppose it's not the case. And this is the type of argument that you're going to use on some of your homework problems. Suppose not. Then what we're going to do is we're going to find the least positive element of A, which is not a multiple of 1. Well, let's first of all set up our set here. A is an A. Suppose A is not a multiple of 1. Let me write this out. The book is not careful right here. They haven't verified that A is a positive element. So we have to check and see what happens. If A is less than 0, then minus A is greater than 0. Now, if there exists an n in the naturals such that minus A is equal to n times 1 sub A, then A has to be equal to minus n times 1 sub A. Just changing the negative on it. Implies that minus A is a multiple of 1. Which contradicts our assumption. So that tells us that A is also not a multiple of 1. And that, the book leaves that whole part out. And they go straight to let C be an A plus, be the least, well, I'm going to say smallest element in A plus, which is not a multiple of 1. Question?
The first part of that, why is the concluding part that A is not a multiple of 1?
Why is it important?
No, why is that so?
Oh,
It contradicts the assumption that it's not a multiple of 1.
I said A is not a multiple of 1. If A is less than 0, then minus A is greater than 0. Let's see, did I lose a minus sign? Okay, so what I'm saying, minus A is, and so A is not, minus A is not a multiple of 1. In other words, what I'm saying is the positive of A is not a multiple of 1 also. If the negative of A is not a multiple of 1, then the positive of A has to also not be a multiple of 1. And I have to go to the positive element because that's the only set I know that has a least element in it. I have to go to the positive sets. So if I'm starting with something negative, then I have to go to the positive. This is where I wish I had cut and paste. I need one sentence in here, so I'll redo this. Thanks for reminding me, though. What your question reminded me I needed one sentence more in here. I know where I'm headed, but I have to get you guys along there. So I'm going to assume that A is greater than 0. Without loss of generality, it doesn't matter if I'm dealing with the negative or the positive of the A. If one of them doesn't have a multiple of 1, the other one will also not have a multiple of 1. And so I need the positive of it. So without loss of generality, A is greater than 0. Let B be equal to the set of all A in A plus, such that A is not a multiple of 1. Then I know that B is a subset of A plus, since A is an ordered, is an integral system. B has a least element. B contains a least element. Let me be very specific. B contains a least element. Call it, what do you want to call it? Call it Y. I know Y minus 1 is not in B. Therefore, by definition of B, Y minus 1 is a multiple of 1. Hence, there exists an M in the integers such that Y minus 1 is equal to M times 1 sub A. Solve that for Y. Now this is also, of course, our 1 sub A that we subtracted. So what does that equal to? It's M plus 1, 1 sub A's, right? What is that saying about Y? Y is a multiple of 1 then, right? But how, Y was in B, and what does it mean for Y to be in B? Yeah, it's not a multiple of 1. So if Y is a multiple of 1 and it's not a multiple of 1, which can't both happen, thus B has to be equal to the empty set. Therefore, every element in A is a multiple of 1. This is an argument you're going to need on your homework. Do what?
The proof box went away.
Oh. Not in an integral system. Hmm?
What about in life?
Oh. Yeah, if you don't have something that's an integral system, then you could have, if you're,
Well, if one
You
was
can
the
multiply any
coefficient,
matrix
yes,
by the
one was
one
like a
matrix.
matrix unity.
yeah, no, on the matrix unity. In other words, could you have something that, I think it would have to be a non-square matrix to be able to get to it. Because then you can't multiply the square matrix, which is your identity. But if you have a square matrix, I don't know. I'd have to ponder that one. I'm sure there are, because we have, if you have something that is not in an integral system. So you'd have to have something that was a rational numbers. If you had matrix of rational numbers, for instance. Or any rational number like 1/2, you can't get to it by multiplying 1 a whole bunch of times together. So if in the ring of rational numbers, that wouldn't work. Okay, every integral system is isomorphic to the integers. This is a homework problem. This is a bit of a tedious homework problem in that it is, you have to show one-to-one and onto, and one-to-one and onto arguments are using this argument that I did right here. Yes, so you're going to have to figure out how to do your one-to-one and onto arguments using the sets like this. So that's where that comes from. So the arguments are similar to the argument in the previous problem. But I'm going to let you struggle with it a little bit before you ask me questions. Since every integral system is isomorphic to the integers, any two systems are isomorphic to each other, and thus, this should have been the integers, not A. Z is, up to isomorphism, the only integral system. Hence the terminology. So we have constructed our integers. Now we need to talk about mathematical induction, and I'm going to actually prove the division algorithm for you guys. K is going to represent the set of positive integers. If 1 is in K, and for any positive integer K, if K is in K, then K plus 1 is in K. This is our principal mathematical induction. And I put both forms of it down here. This is the one that I like to use, identifying S1, S2, Sn, or P of n is a statement that I usually use on it. But that's the form I use. Our division algorithm, this says if m and n are integers and n is positive, there exist unique integers q and r such that m is equal to q plus r, 0 is less than or equal to r is less than n. Q is a quotient, r is a remainder in the division of m by n. So the hypothesis, let m and n be integers where n is going to be greater than 0. I have to find integers q and r so that m is equal to nq plus r. So what the book does is they first start writing down a multiple of n. So what we're going to do is we show first that there exists an x in the integers such that xn is less than or equal to m. That's going to be the first step. Then they're going to subtract it. They'll get m minus xn. Now n is positive, so what does that tell you? Yeah, n has to be greater than or equal to 1, right? If n is positive, n is greater than or equal to 1. Now m could be either positive or negative. M is less than 0 or m is greater than or equal to 0. Those are my cases. So let's look at the cases separately. And the first case the book does is m is greater than or equal to 0. If m is greater than or equal to 0, I know that 0 is less than or equal to m, and multiply both sides by x. So you're going to have 0x, I want x0, is less than or equal to x times m for all x in the positive integers. Okay? As desired. Now, our case 2. M is going to be less than 0. If m is less than 0, then what do we get? Well, yeah, q from up there is negative. Yeah, we're getting to that. Then multiply both sides of n greater than 1 by minus m. And what do you have? Maybe I should ask the question that way. If you multiply both of those by minus m, you're going to have minus m times n is greater than or equal to minus m times 1, right? This tells you that minus m is greater than or equal to 0. If m is less than or equal to 0, minus m is greater than or equal to 0, and you multiply both of those. But how does that help me? Add to both sides mn plus m. I have minus mn greater than or equal to minus m times 1, which is our minus m. And add to both sides mn plus m. Mn plus m. And what do you get? And so for x equal to n, I have my equation where I wrote it down what I was trying to show. If x is equal to m right here, I have my inequality. There's less than or equal to. Let me get my inequality written down right, as desired. So in both cases, I get this inequality, xn is less than or equal to m. Now what we're going to do is define our set W, and they put this in words. I'm going to put it in here. All t in the integers such that t is equal to m minus xn for some x in the integers. Okay, it's going to be in this form. I have one more part to show after this, so we'll start here next time. They leave out one very important part showing uniqueness of it, so we'll start here next time for deriving our division algorithm. Make sure you turn in your papers.